Strap in, cosmic adventurers, as we embark on a magnetic odyssey to unravel the invisible forces of cosmic magnetic fields, the unseen architects shaping the universe's grandest structures. Welcome to a thrilling exploration of magnetism in space, where we'll dive into the powerful currents weaving through stars, galaxies, and the vast voids beyond, driving everything from star formation to cosmic ray journeys. How do these invisible fields sculpt the cosmos? What role do they play in the birth of planets and the dance of galaxies? And what cutting-edge discoveries are revealing their secrets? Get ready for an electrifying journey packed with mind-bending science, awe-inspiring revelations, and cosmic mysteries that will keep you magnetized to every word. Let's plunge into the role of magnetism in space and uncover the power of cosmic magnetic fields together. Picture the universe as a vast tapestry, woven not just with stars, galaxies, and dark matter, but with invisible lines of magnetic force threading through every corner of the cosmos. These cosmic magnetic fields, generated by moving charged particles, are omnipresent, from the surfaces of stars to the sprawling filaments of the cosmic web. Measured in microgauss to milligauss, far weaker than a fridge magnet's Gauss but stretching across light years, they exert profound influence. In our Sun, magnetic fields drive solar flares, hurling particles that paint Earth's auroras. In galaxies, they guide gas clouds to birth stars and channel cosmic rays along spiral arms. In the intergalactic void, they trace the universe's structure, mapping unseen matter. Unlike gravity, magnetism is a polarized force, aligning particles and shaping plasma, the ionized gas dominating space. As we venture deeper, you'll see how these fields, studied through radio waves and polarized light, reveal the universe's dynamic history and fuel its evolution. Doesn't the idea of invisible forces steering the cosmos spark your curiosity to learn more? The story of cosmic magnetic fields begins with their discovery, rooted in early 20th century astronomy. In 1908, George Ellery Hale observed Zeeman splitting, spectral lines splitting in magnetic fields, in sunspots, proving the sun's magnetism. By the 1940s, radio astronomy revealed polarized emission from the Milky Way, hinting at galactic fields. Hannes Alfvén, a Swedish physicist, pioneered magnetohydrodynamics, or MHD, describing how magnetic fields interact with plasma. His 1970 Nobel Prize recognized this, explaining solar and stellar phenomena. In 1953, Enrico Fermi and Subrahmanyan Chandrasekhar proposed cosmic rays were confined by galactic fields, a theory confirmed by 1980 synchrotron maps, radiation from electrons spiraling in magnetic fields. By 2025, observatories like the Square Kilometre Array and ALMA map fields across galaxies, using Faraday rotation, where polarized light twists in magnetized plasma. This journey from sunspots to cosmic webs shows magnetism's universal reach. How did a solar clue unveil a cosmic force? Magnetic fields arise from dynamo processes, where moving conductive fluids generate currents. In stars like the Sun, differential rotation, faster equator, slower poles, twists convective plasma, amplifying fields to 10,000 Gauss in sunspots. The solar dynamo cycles every 11 years, driving flares and coronal mass ejections, observed by SOHO in 2025. In galaxies, turbulent gas motions and rotation create microgauss fields, strongest in spiral arms at 10 to 50 microgauss. The Milky Way's field, mapped by Gaia's 2025 polarimetry, follows its spiral, guiding gas. In clusters, fields reach 1 to 10 microgauss, shaped by mergers, detected by Chandra's X-ray synchrotron. Intergalactic fields, at nanogauss, arise from primordial fluctuations or early star feedback, traced by fast radio burst rotations in 2025. These dynamos, from stellar cores to cosmic voids, show magnetism's scalability. What powers these cosmic magnets? In star formation, magnetic fields are pivotal. Molecular clouds, 10 light-years wide, collapse under gravity to form stars, but magnetic fields resist, channeling gas via field lines. ALMA's 2025 images of Orion's clouds show hourglass-shaped fields, 100 microgauss, slowing collapse. This regulates star formation rates, explaining why only 1% of gas forms stars. Magnetic pressure supports clouds against gravity, while ambipolar diffusion, neutral gas slipping past ions, allows slow collapse. Protostellar disks, like HL Tauris, seen by JWST in 2025, have fields shaping jets, collimated outflows at 100 km per second, carving bipolar structures. These jets disperse angular momentum, enabling accretion. Magnetism thus midwives stars. How does it balance creation and resistance? In galaxies, magnetic fields orchestrate structure. The Milky Way's 5 microgauss field, mapped by Planck's 2025 polarimetry, aligns with spiral arms, guiding gas into star-forming regions. Synchrotron emission, from relativistic electrons, traces field strength, while Faraday rotation reveals direction. In starburst galaxies, like M82, fields reach 100 microgauss, amplified by rapid star formation. Magnetic torques transfer angular momentum, stabilizing disks. Cosmic rays, confined by fields, exert pressure, inflating galactic halos, seen in NGC 4631's radio halo. In 2025, Meerkat surveys show field reversals in spirals, hinting at dynamo cycles. These fields shape galactic evolution, linking stars to large-scale structure. How do they choreograph galactic dances? In galaxy clusters, magnetism intensifies. The Virgo cluster's 1 to 10 microgauss fields, detected by XMM Newton synchrotron, arise from turbulent mergers. Hot intracluster plasma, at 10 to the power of 8 Kelvin, conducts fields, amplifying them via shear flows. Radio relics, like those in Able 2256, show shock-accelerated electrons glowing in fields. Faraday rotation maps, from 2025 Zeta data, reveal turbulent fields spanning megaparsecs. These fields influence cluster dynamics, heating gas and confining cosmic rays, impacting star formation in member galaxies. Magnetism thus sculpts the universe's largest bound structures. What role does it play in cosmic giants? Intergalactic fields, at 10 to the power of -9 Gauss, are faint but vast. They trace the cosmic web, filaments, walls, and voids, detected via FRB rotations by CHIME in 2025. Primordial fields, from Big Bang fluctuations, or astrophysical feedback, like AGN jets, seed them. Simulations, like Illustris TNG, show fields growing via galaxy outflows. These fields affect cosmic ray propagation, deflecting UHICers, and magnetize voids, probed by Fermi lattice gamma-ray pairs. They test cosmological models, constraining early universe physics. How do these faint fields map the cosmic web? Cosmic rays, protons, and nuclei at 10 to the power of 9 to 10 to the power of 20 eV, are guided by magnetic fields. In the Milky Way, fields trap rays for millions of years, producing synchrotron emission, seen by LOFR in 2025. Extragalactic rays, deflected by cluster fields, lose directionality, complicating source identification. Auger's 2025 data shows Uhicra's bending less, hinting at nearby sources like Centaurus A. Fields also drive plasma instabilities, accelerating particles via Fermi processes. Magnetism thus links cosmic rays to their explosive origins. How does it steer these cosmic bullets? In the solar system, magnetism shapes space weather. The Sun's 1 to 10 Gauss field, peaking at 10,000 in sunspots, drives flares, releasing 10 to the power of 32 ergs, impacting Earth. The heliosphere, a $100 bubble, shields us from galactic rays, with Voyager 2's 2025 data measuring its 0.1 microgauss boundary. Earth's 0.5 Gauss field deflects solar wind, creating auroras, seen in 2025's solar maximum. These fields protect life, but astronauts face risks, with Artemis shielding tests ongoing. How does magnetism guard our world? Detection is a technological triumph. Radio telescopes, like SKA, map synchrotron emission, tracing field strength. Polarimetry, via Planck and Gaia, measures field direction through starlight alignment. Faraday rotation, using FRBs, probes field geometry. X-ray synchrotron, from Chandra, reveals cluster fields. In 2025, CTA's gamma-ray polarimetry tests primordial fields. Challenges include separating astrophysical signals from noise, requiring machine learning. Future missions, like SphereX, will map all sky fields. What will these tools unveil? Mysteries persist. What seeded primordial fields, Big Bang or early stars? Why do galactic fields reverse? Can intergalactic fields explain Uhicra deflections? Do they influence dark matter dynamics? Rubin's 2025 to 2035 surveys may detect lensing by magnetized filaments. These questions drive research, with answers looming. Future prospects excite. SKA's 2025 phase maps million galaxy fields. Athena's 2030 X-ray polarimetry probes AGN jets. LISA's gravitational waves, by 2035, may detect magnetized mergers. If we map primordial fields, we'll probe the Big Bang. What breakthrough awaits? What does magnetism mean for us? It shapes stars, galaxies, and life's cradle. Your auroras, sparked by solar fields, tie to cosmic currents. From Hale's sunspots to SKA's maps, curiosity unveils them. We're cosmic navigators, riding magnetic waves. As we near the end, let's gaze ahead. Cosmic magnetic fields, invisible architects, sculpt the universe's story. New telescopes, data, and dreams will decode them. What fields shape distant galaxies? How will they redefine our cosmos? The universe hums, full of wonder. What questions stir your mind? Thank you for joining me on this epic dive into the role of magnetism in space, cosmic magnetic fields. I hope your curiosity blazes. If you loved this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about cosmic magnetism? What mystery should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Adventurers.